corollary 1. Let A and Q be the matrices that are conformable for multiplication. Then we have to show that column rank of multiplication of these two matrices is less than equal to column rank of A. Second, column rank of multiplication of these two matrices is equal to column rank of A if Q is non-singular. So for Q to be non-singular, we get the equality, right? Okay. So let's start with the proof. For the first part, let's take A to be a matrix of the form Aij of the type m by n, which can be written in the column format as C1, C2, C3 up to Cn. And let Q be the matrix, let's say Qij of the type n by p, right? And then multiplication of these two matrices, that is writing A as in the column format C1, C2, C3 up to Cn, and writing Q matrix in the matrix form as the element present in the first row, first column, the element present in the first row, second column, the element present in the first row, third column, so on. How many columns are there? P columns. So it is Q1P, right? Similarly, the element present in the second row, first column, in the second row, second column, in the second row, third column, so on, in the second row, pth column, right? Likewise, how many rows are there? N rows. So the element present in nth row, first column, nth row, second column, nth row, third column, nth row, pth column, right? Now let's multiply these two matrices. We get Q11C1 plus Q21C2 plus Q31C3, so on, Qn1Cn. Then is Q12C1 plus Q22C2 plus Q32C3, so on, Qn2Cn. And at the last, we get Q1PC1 plus Q2PC2 plus so on, QnPCn. So this shows that the column of this AQ is a linear combination of C1, C2, C3 up to Cn, and consequently lie in the column space of A. So the column of AQ is linear combinations of C1, C2 up to Cn, and consequently lie in the column space of A. So therefore, column space of AQ is a subset of column space of A. This implies the dimension of column space of AQ is less than equal to the dimension of column space of A. And dimension of column space of AQ is nothing but column rank of AQ, which is less than equal to the column rank of A. Now this column rank of AQ will be equal to column rank of A if Q is non-singular, right? So for the second part, let Q be non-singular. And from the first part, we know that column space of AQ is a subset of column space of A. Also, I can write the column space of A to be equal to column space of A into I, where I is the identity matrix. Now because Q is non-singular, it is given to us. So I can write the identity matrix as the product of Q and Q inverse. Because Q is non-singular, that is given to us, right? So this is equal to column space of taking this AQ together. This is Q inverse. And because from the first part we know that column space of multiplication of these two matrices is a subset of column space of the first matrix, that is AQ. So from here we say that column space of A is a subset of column space of AQ. Please mark this as 2 and also mark this as 1. So one says that column space of AQ is a subset of column space of A. And 2 says that column space of A is a subset of column space of AQ. So from 1 and 2, we get column space of AQ is equal to column space of A, where Q is a non-singular matrix. Alright, so whenever the column space of the matrices are equal, their dimensions are also equal. Dimension of column space of AQ is nothing but column rank of AQ. This is equal to dimension of column space of A, that is column rank of A. Hence the result. Thank you.